Dear students, after studying this module, you will be able to know about the important instrumental techniques for drug analysis, the basics of instrumentation, and drug detection by specific instrumental techniques. First, introduction to high performance thin layer chromatography, that is HPTLC. Principle: in thin layer chromatography, constituents of a mixture are separated on thin uniform surface of solid stationary phase, which is usually silica, coated on glass or aluminium or plastic plate. Help of moving liquid phase. The mobile liquid phase migrates or ascends on solid stationary phase by capillary action, carrying the different analyte molecules of a mixture with different speed depending upon their affinity for stationary phase. In this process, the constituents, that is the analytes, are separated into fractions. After development of the chromatogram to a certain distance, the thin layer chromatography plate is removed and mobile phase is evaporated. The track is scanned in a densitometer with a light beam in visible or ultraviolet range of the spectrum. Depending upon the mode of scanning, absorbance or fluorescence is measured by diffuse reflectance. Equipment of HPTLC. First are the TLC plates, normal phase TLC plates. In normal phase TLC plate, analytes are primarily isolated as per their polarity and their solubility for the mobile phase. The chemical constituents in the normal phase TLC are of silica gel with gypsum as a binder to increase the mechanical strength of silica gel. Second is reversed phase TLC plates. Because of the interest in reversed phase plates, HPLC pre-coated reverse phase TLC plates are available with C18, C8, C2 and phenyl groups chemically bonded onto a silica support to produce stationary phases. Next is HPTLC plates. HPTLC plates have the layer of stationary phase particles of size 3 to 7 micrometers with a thickness of 20 millimeters. Due to insignificant size of the particles and higher surface area, HPTLC plates show less lateral spreading and hence the concentration in the spot is higher, which makes the analyte easy to identify and increase the sensitivity. Next is sample application. Sample is applied either manually using capillary tube in the form of spots or automatic TLC sampler in the form of narrow bands using spray technique. Narrow bands at starting zone confirm the maximum resolution. Next is development chamber. After application of sample plate is settled in even bottommost twin trough horizontal or automatic development chamber. Next is automated multiple developments, that is AMD. The advantage of multiple developments is that it is helpful in improving the separation of analytes with low RF values. In the AMD procedure, fractions are focused into narrow bands with characteristic peak width of about 1 mm, so that on available separation distance of 80 mm on a HPTLC plate, up to 40 constituents can be resolved, that is with baseline separation. Next is the scanner or the densitometer. For densitometry assessment of a HPTLC chromatogram, the path is scanned with the help of a beam of light in the form of a slit which is selectable in both width and length. Diffusely reflected light is measured with photosensor, that is photomultiplier. Next are the applications of HPTLC. First, qualitative analysis. RF values are estimated and matched with the control samples. To avoid the use of decimals In these values, it is multiplied by 100 and the values are then referred to as HRF. Second is in situ spectra, that is absorbance versus wavelength of the analyte, and standard reference material are recorded and compared. Next are the quantitative analysis. For quantification, the dissimilarity in optical signal from the sample freeze circumstantial and that from a sample zone fractions correlated with the amount of the respective fractions of calibration standards chromatographed on that plate. Densitometry scanning measurement can be made in absorbance or fluorescence mode by measuring diffusely reflected light. Alternatively to classical densitometry, planar chromatography can be evaluated by video technology. Additional operations such as pre and post chromatographic dramatizations can be performed as required. For quantitative analysis in absorbance mode, Beer-Lambert's law is applied. A or log of I by IO is equal to ABC, where A is absorption coefficient, B is path length and C is concentration, and A is the absorbance. Next technique is gas chromatography. Gas chromatography, precisely gas-liquid chromatography, includes a tester being evaporated and inserted onto the head of the chromatographic column. The tester is passed over the column with the movement of inert gaseous mobile phase. The column comprises of the stationary phase, that is the liquid, that is absorbed by the inert solid onto its surface. Next are the instrumental components. First is the carrier gas. The gas that is used as a carrier must be chemically inert and mainly comprise of gases such as nitrogen, helium, argon and carbon dioxide. The selection of carrier gas is basically reliant on the form of detector which is used. The carrier gas system also comprises a molecular sieve to eliminate water and other contaminations. Next is sample injection port. The most customary injection technique is where a microsyringe is used to insert tester by a rubber septum into a flash vaporizer port at the head of the column. The temperature of the tester port is generally about 50 degrees Celsius higher than the boiling point of the least volatile component of the sample. In case of packed columns, the sample size varies from 1 by 10 to 1 by 20 microliters. Capillary columns, on the other hand, require much less sample. Characteristically, around 10 raised to power minus 3 ml for capillary GC split or splitless injection is used. The injector comprises a heated chamber covering a glass liner into which the sample is inserted by the septum. The carrier gas goes in the chamber and can get out by 3 ways when the injector is in split mode. The sample evaporates to form a combination of carrier gas, vaporized solvent and vaporized solutes. An amount of this combination passes onto the column, but most departure from the split outlet. The septum purge outlet stops septum bleed constituents from inflowing the column. Next are the columns. There are two usual kinds of column, packed and capillary, also called as open tubular. Packed columns are formed by using materials that are inert, finely divided, having solid support component comprising of diatomaceous earth covered with liquid stationary phase. The length of these columns varies from 1.5 to 10 meters and the internal diameter of the column varies from 2 to 4 millimeter. Capillary columns have an internal diameter of a few tenths of a millimeter. They can be one of the two kinds, wall-coated open tubular or WCOT or support-coated open tubular SCOT. WCOT columns contain a capillary tube wherein the walls are covered with a stationary phase that is liquid. In support-coated columns, the inside of the capillary tube is coated with a thin film of diatomaceous earth that acts as a support material and the stationary phase is adsorbed on it. These types of column are usually less effective than the wall-coated open tubular columns. Both types of capillary column are more efficient than packed columns. In 1979, a new type of WCOT column was devised, the fused silica open tubular or the FSOT column. These have much thinner walls than the glass capillary columns, and in this strength is provided by the polyimide coating. These columns are flexible and can be wound into coils. They have the advantages of physical strength, flexibility, and low reactivity. Next is column temperature. For precise work, column temperature must be controlled within tenths of a degree. The boiling point of the sample determines the optimum column temperature. As a rule of thumb, a temperature slightly above the average boiling point of the sample results in an elution time of 2 to 30 minutes. Good resolution can be obtained by increasing the elution time but having minimum temperature. If a sample has a wide boiling range, then temperature programming can be useful. The column temperature is increased either continuously or in steps as separation proceeds. Next are the detectors. There are many detectors which can be used in gas chromatography. Various kinds of selectivity can be obtained by using various detectors. A non-selective detector retorts to all compounds apart from the carrier gas. A selective detector responds to a variety of compounds with a common physical or chemical property. And a specific detector responds to a single chemical compound. These can be classified into concentration dependent and mass flow dependent detectors. Concentration of solute is directly related to the signal given by the concentration dependent detector, and hence the sample is not generally destroyed. Dilution with makeup gas will lower the detector's response. The signal from the mass flow dependent detectors is related with solute molecules rate at which they enter the detector, and thus in this the sample gets destroyed. The response of a mass flow dependent detector is unaffected by makeup gas. Now let us have a look at this tabular summary of common GC detectors. Detector, type, support gases, selectivity, detectable limit and dynamic range. First is flame ionization detector, that is FID. Type is mass flow, support gases are hydrogen and air, and selectivity is most organic compounds. Detectable limit is 100 picograms and dynamic range is 10 raised to power 7. Next is thermal conductivity detector. Type is concentration, support gases reference, selectivity universal, and detectable limit is 1 nanogram and dynamic range is 10 raised to power 7. Next is electron capture detector. Type is concentration, support gases makeup, selectivity halides, nitrates, nitriles, peroxides, anhydrides and organometallics. Detectable limit is 50 Fg and dynamic range is 10 raised to power 5. Next is nitrogen phosphorus detector. The type is mass flow. Support gases are hydrogen and air. Selectivity is nitrogen and phosphorus. Detectable limit is 10 picograms and dynamic range is 10 raised to power 6. Next is flame photometric detector. The type is mass flow. Support gases are hydrogen and air and possibly oxygen. The selectivity is sulfur, phosphorus, tin, boron, arsenic, germanium, selenium and chromium. Detectable limit is 100 picograms and dynamic range is 10 raised to power 3. Next is photoionization detector. Type is concentration. Support gases make up. Selectivity aliphatic, aromatics, ketones, esters, aldehydes, amines, heterocyclic, organosulfur and some organometallics. Detectable limit is 2 picograms and dynamic range is 10 raised to power 7. Next is Hall electrolytic conductivity detector. Type is mass flow. Support gases are hydrogen and oxygen. Selectivity is halide, nitrogen, nitrosamine and sulfur. The effluent from the column is mixed with hydrogen and air and ignited. Organic compounds form electrons and ions when introduced to flame, and that also results in conduction of electricity. The collector electrode is situated just above the flame, thereby resulting in the production of large electrical potential at the burner tip. FIDs are mass sensitive rather than concentration sensitive. Hence, the detector's response is not affected by the flow rate of mobile phase. The flame ionization detector is useful for the study of organic compounds due to its high sensitivity, low noise and large linear response range. It is also robust and easy to use, but unfortunately it destroys the sample. Next is high performance liquid chromatography. HPLC instrumentation includes a pump, injector, column, detector and recorder or data system. The heart of the system is the column where separation occurs. A high pressure pump is needed so as to move the mobile phase through the column, as the stationary phase comprises of micrometer size porous particles. The chromatographic process begins by injecting the solute onto the top of the column. Separation of components occur as the analytes and mobile phase are pumped through the column. Eventually, each component elutes from the column as a narrow band or peak on the recorder. Detection of the eluting components is important, and this can be either selective or universal, depending upon the detector used. The response of the detector to each component is displayed on a chart, recorder or computer screen. To collect, store and analyze the chromatographic data, computers, integrators and other data processing equipment are frequently used. Next is mobile phase reservoir and filtering. The most common type of solvent reservoir is a glass bottle. So as to remove the dissolved air purge gas or helium is used, and Teflon tubing and filters are employed to connect it to the pump inlet. Next is solvent delivery system. High pressure pumps are generally used to move solvents by force through the packed stationary phase beds. Flow rate stability is an important pump feature. An added feature found on the more elaborated pumps is external electronic control. Although it adds to the expense of the pump, external electronic control is a very desirable feature when automation or electronically controlled gradients are to be run. It is desirable to have an integrated degassing system, either helium purging or vacuum degassing. Next are the columns. Typical LC columns are 10, 15 and 25 cm in length and are fitted with extremely small diameter. that is 3, 5 or 10 mm particles. The inner diameter of the column is generally 4 to 4.6 mm, and this is considered as the suitable condition for speed, mobile phase consumption and resolution and sample capacity. However, if pure substances are to be collected preparative scale, larger diameter columns may be needed. Next are the detectors. In case of liquid chromatographic system, optical detectors are usually employed. These detectors pass a beam of light through the flowing column effluent as it passes through a low volume flow cell. The variations in light intensity caused by UV absorption, fluorescence emission or change in refractive index depending on the type of detector used from the sample components passing through the cell are monitored as changes in the output voltage. These voltage changes are recorded on a strip chart recorder and frequently are fed into an integrator or computer to provide retention time and peak area data. The most commonly used detector in liquid chromatography is the ultraviolet absorption detector. This variable wavelength detector is adept at monitoring from 190 to 460 to 600 nanometer and hence is suitable for detection of samples. Other detectors in common use include refractive index, fluorescence, electrochemical conductivity, photodiode array and mass spectrometric detectors. The RI detector is universal but also the less sensitive one. Fluorescence and electrochemical conductivity detectors are quite sensitive but also quite selective. The MS detector is the most popular one for the identification. Next are the injectors. Sample introduction can be accomplished manually or by auto samplers. In liquid chromatography, liquid samples may be injected directly and solid samples need to be dissolved in an appropriate solvent, preferably mobile phase. It is essential to remove particles from the sample by filtering or centrifuging since continuous injections of particulate material will eventually cause blockage of injection devices or columns. Next is data station. The data station consists of a PC, an integrator or printer that in addition to revealing the chromatograms stores and monitors various parameters related to the system. The PC selected should be compatible to the main system. Next is UV visible spectroscopy. Absorption spectrometry in the UV visible regions is considered to be one of the oldest physical methods used for quantitative analysis and structural analysis. The law of absorption of radiant energy with which the analyst is concerned involves the relationship between the magnitude of absorption and the quantity of absorbing material present in solution. These laws are applicable to absorption of energy in any region of the spectrum. Next is Beer-Lambert's law. It states that the proportion of light absorbed by a transparent medium is independent of the intensity of the incident light and that each successive layer of the medium absorbs equal fraction of the light passing through it. This can be expressed mathematically as log of IO by I is equal to Ki, where IO is intensity of the incident light, I is intensity of the transmitted light and T thickness of the layer in centimeters, alpha absorption coefficient of the medium and K constant depending only on the medium examined and is known as extinction coefficient. Next is Beer's law. The absorption coefficients alpha and K contain no concentration factor and Beer's law deals with this variable. According to this law, the light absorbed is proportional to the number of molecules of absorbing substance through which the light is passed, if the absorbing substance is dissolved in a transparent medium. The absorption of the solution will be proportional to its molecular concentration. Next is Beer-Lambert's law. The combined law may be expressed as log of IO by I is equal to molecular extinction coefficient Ci, where molecular extinction coefficient is eta and C is the concentration in gram moles per liter. The validity of the combined law should be tested for each system, which is being quantitatively investigated. It is simply necessary to prepare a series of known concentrations of the substance being measured and determine the absorbance at a particular wavelength. The values may be plotted against concentration, or the molecular extinction coefficient may be attributed to a deviation from Beer's law. Beer's law is a limiting law for dilute solutions. Qualitative applications. Specific identification of a compound can rarely be made on the basis of spectral evidence alone. Often the spectrum serves as confirmatory evidence of identity in support of other analytical data. Spectra are recorded in aqueous, acidic, basic and ethanolic or methanolic solution. The wavelengths of the principal peaks and the corresponding absorptivity values are noted for each solvent system. By comparison with data tabulated in ascending wavelength order, a number of compounds with absorbing properties. Spectral shifts are among the most useful diagnostic features in drug molecules possessing ion groups. A marked bathochromic shift in alkaline solution is observed not only for most of the phenolic drugs such as the phenolic estrogens, but also in the case of hydroxyl pyridines, ketones, benzodiazepines, pyridines and nitro compounds. Next is infrared spectrometry. Infrared spectrometry is the study of the reflected, absorbed or transmitted radiant energy in that region of the electromagnetic spectrum from wavelength lambda 0.8 to 500 micrometers. A more commonly used measurement than wavelength is the frequency, the number of waves per unit. This is expressed in wave numbers, that is centimeter inverse. The infrared spectrum is usually divided into three regions: 12,500 to 4,000 centimeter inverse, that is 0.8 to 2.5 micrometers near infrared, 4,000 to 400 centimeter inverse, that is 2.5 to 25 micrometers mid infrared, and 400 to 20 centimeter inverse, that is 25 to 500 micrometer far infrared. Only the mid infrared region, usually referred to simply as infrared, is considered here because it is the region which is widely used in the analysis of drugs and pesticides. When a molecule is subjected to infrared radiation, transitions take place between rotational and vibrational energy levels in the ground electronic state. These transitions give rise to an absorption spectrum characteristic of the compound. This is in contrast to ultraviolet radiation, which also causes transitions between rotational and vibrational energy levels. But because of its greater energy, these transitions occur at higher energy states. In the infrared, absorption occurs only where a change of the dipole moment of a molecule can take place. This means that diatomic molecules without dipoles such as hydrogen, nitrogen and oxygen do not absorb in the infrared. Total symmetry about an absorption band will eliminate certain absorption. Example, the symmetrical ethane molecule give no carbon-carbon stretching absorption bands. Three main types of absorption occur, namely fundamental, overtone and combination. Fundamental bands are the primary absorption bands for each mode of vibration. Overtone bands occur at multiples of the fundamental band wavelength, and combination bands occur at wavelengths which are the sum or difference of two or more fundamental bands. Overtone and combination bands are usually much weaker than fundamental bands. Particular bonds or functional groups in a molecule have specific absorption bands at given wave numbers. Changes in the wave number of a band have been correlated with changes in either the structural environment or the physical state of the molecule. These correlations form the basis of qualitative analytical work in infrared spectrometry. However, many bands in the complex region from 1600 to 400 centimeter inverse, which is usually referred to as the fingerprint region, are still of unconfirmed origin. A proportion of the bands is characteristic of the molecule as a whole and cannot be assigned to particular functional groups. HPTLC is advanced technology which is fundamentally based on TLC principle but gives better results than TLC method. HPTLC results come in the form of chromatograms which can be helpful in qualitative and quantitative examination. Gas chromatography is the basic technique for volatile drugs and can be used with many detectors which can be selected on the basis of sample which has to be analyzed. UV visible spectroscopy gives quantitative results of the investigated material. Infrared spectrometry is also known as fingerprint of molecules and gives very accurate results for pesticides and drugs.